Greetings everybody, and today we're going to be evaluating this very spicy looking integral from 0 to 3 of all of this junk, and we're going to be using something called the Dogbone contour, which I haven't covered on this channel yet, but it is a very interesting contour to work with. So this is actually an example straight from Wikipedia. The solution they give on Wikipedia to this integral isn't the best. It took me quite a while to fully understand the solution, but yeah, finally understand now, and I'm here to present it to you today. Kind of my take on it. Before we get started, only a small proportion of my viewers are actually subscribed to my channel, so if you find my content helpful, then consider subscribing. I make this content for free and your support is much appreciated. And I'm pretty close to hitting 1,000 subscribers, so yeah, subscribe. So we have this integral from 0 to 3. It's a little bit weird because usually in complex analysis we're working with improper integrals, but we have this integral and we want to take a look at this function, and we're going to call the integrand some function f of z. So we're going to let f of z be equal to the integrand, but we're going to replace all the x's with z, so we're jumping into the complex plane now. So z to the 3/4, 3 minus z to the 1/4, over 5 minus z, like so. And we want to notice one thing over here. Notice that we have fractional powers, and whenever you have fractional powers, you are going to have branch cuts because these functions aren't in fact continuous everywhere. You're going to have branch cuts, and we want to define the branch cuts in a way such that it's useful to work with. So step 1 to this video, step 1 is going to be studying this numerator. So we're going to have a look at z to the 3/4 and then 3 minus z to the 1/4. And let's actually rewrite this a little bit. This is going to be equal to e to the 3/4 natural log of z, and then e to the 1/4 natural log of 3 minus z. And I've done a video of logarithms of complex numbers. If you have the natural log of a complex number z, it's going to be the natural log of the modulus of z. So this is going to be the real part, and then you're going to have plus I times the arg of your complex number z. So let's use this definition of the complex logarithm for these parts. So this is now equal to e to the 3/4 natural log of the absolute value of z, and then we're going to have plus I times 3/4 times the argument of z. And for the second part, we're going to have e to the 1/4 natural log of the absolute value of 3 minus z, and then plus I times 1/4 the argument of 3 minus z, like so. Right, now I want to clean things up a little bit, maybe combine a couple terms here and there. Notice that we can split these exponentials up. So we're going to have another e over here and another e right here. And notice this part and this part, we can reduce that back down to just being the absolute value of z to the 3/4. So absolute value of z to the 3/4. And then over here, similarly as well. So we have 3 minus z to the 1/4. And now we just have these arguments to play around with. Let's combine those two together. So we're going to have e. And then notice we have a common factor of I times 1/4. So we have I times a quarter. And then inside some brackets, we're going to have 3 times the arg of z, and then we're going to add arg of 3 minus z. So this is what we have over here. This is an equivalent expression, and the nice thing with writing it this way is we have it in polar form, kind of, because this is the modulus, and we have e to the I times some kinds of angle, and this angle over here is what we want to specifically study because the modulus is continuous everywhere, but these argument functions aren't, and that's what we want to kind of mess around with. So these arguments function, let's just take a look at it on the complex plane. For just arg of z, we're going to have some kind of branch point at the origin, and then we can choose literally any branch we want that's going in any direction. And we also have arg of 3 minus z. Well, 3 minus z, you can kind of think about this as minus z minus 3. So we have a minus 3, so we're shifting everything to the right by 3, and we have a minus, so in fact everything's kind of reversed, but we're still over here at 3, and we can again choose any branch we want. And what is the best branch to choose for both of these? Well, we want to choose a branch such that when we kind of add these together, it produces one branch cut along this interval 0 to 3. And the idea is we're going to be integrating around this branch cut. So we don't want branch cuts that are going out to infinity or whatever, because those are a little bit more tricky to deal with. So how do we produce this branch cut? Well, the idea is for the branch at 0, we're going to be choosing a branch that's going along the negative real axis, like so. And for the branch at the point 3, what we want to do is we also want to choose a branch that's going along the negative real axis, like so. But what's actually going to happen, a really nice thing is going to happen, these two, when you kind of multiply these two together, they're going to cancel out, and everything in between here is going to be nice and continuous, and you're left with a single branch cut along 0 to 3. And we're going to show how we can do that right now. So notice that the argument is given by, well, we have e to the I and whatever's over here, so it's exactly 1/4, and then 3 arg of z plus arg of 3 minus z. And what we want to do is we're going to define arg of z to just be on the principal argument, so from minus pi all the way up to pi. And we're going to define arg of 3 minus z. It's going to be a little bit more strange, but we're going to go from 0, then this is less than arg of 3 minus z, and this is going to go all the way up to 2 pi, like so. And this is pretty obvious because we want the branch over here to be on the negative real axis. It's not so clear over here, but because remember we had this kind of reorientation over here, even though we're kind of going from 0 to 2 pi, that's just if we have z minus 3. If we chuck an extra negative sign over here, then it's going to reverse the whole thing, and we're going to go in this direction, which is exactly what we want. And now what we want to show is that we are continuous, the argument function is continuous on this interval from minus infinity up to 0. So we want to take a look at the interval minus infinity to 0 right now, and we want to see what happens as we approach this interval from above. So approaching from above, what are we going to get? Well, notice that arg z will definitely approach pi, because if we look at this picture again, minus infinity to 0 is this interval, and if we're approaching from above, then arg z is obviously going to approach pi. And how about arg of 3 minus z? So arg of 3 minus z. This is a little bit more tricky to think about, because what exactly are the values of 3 minus z? Well, minus z is going to be on 0 to infinity, so just reversing this. And then 3 minus z is going to be on 3 comma infinity, so we're just adding 3. So what happens as we approach this from above? Well, notice for our z, we can decompose this into x plus I, y. If z is approaching this branch from above, that means our imaginary part is reducing. So if we consider this interval 3 to infinity over here, if our imaginary part is reducing over here, it's getting smaller and smaller and smaller. Because we have negative in front of the z, we're going to initially start negative, and we're going to reduce our imaginary part like so. And notice the argument of 3 minus z. So this picture over here is the picture of 3 minus z. If this imaginary part is reducing, then what happens is that the argument will approach 2 pi, because this is 0 and then pi. And then as we approach that branch cut from below, we're going to approach 2 pi. So this is going to approach 2 pi. All right, and what does that mean overall? That means the argument function from above will approach 1/4, and then we have 3 times arg of z, which is 3 pi, and then plus 2 pi, like so. And the argument function will approach 5 pi over 4. So this is quite important, so I'm going to draw a picture over here. So this is 0, this is 3. On the interval minus infinity to 0, approaching from above, our argument will approach 5 pi over 4. Alright, and how about from below? Well, arg of z, if we approach that interval from below, it's definitely going to approach minus pi. And the tricky thing now is, how about arg of 3 minus z? What is that going to approach? Well, again, if z is approaching this interval from below, so z is equal to x plus I, y. If it's approaching from below, we have a negative imaginary part and it's shrinking down. So 3 minus z, if we draw that picture, 3 minus z, again, that's going to be defined on this interval over here. And because we have a minus z and our imaginary part is positive, in fact, the imaginary part of this whole 3 minus z will initially be positive, and it's going to be reducing down all the way to 0. So it's going to go this way. And if you take a look at the argument of that, it's going to be approaching 0. So this is going to be approaching 0. All right, and what does that mean for the whole argument itself? It's going to approach 1/4, and then we have 3 times arg of z, which is minus pi, so minus 3 pi, and then plus 0. And this is equal to minus 3 pi over 4. So approaching this from below, we're going to get minus 3 pi over 4, like so. And you may notice that these two arguments are in fact equivalent because if you have e to the I 5 pi over 4, it's the exact same thing as e to the minus I 3 pi over 4. And that's exactly what we're going to have over here. So in fact, on the interval minus infinity to 0, if we define the argument of both branches in this way, then the argument function is continuous on that interval. And now I want to show that the interval from 0 to 3 is discontinuous. So now let's take a look at 0 to 3. You can kind of see quite clearly because on our picture before we had one branch going this way, another branch going this way, and of course there's only one branch cut here, so of course it's going to be discontinuous. But we want to show this because it's going to be useful later on. So approaching from above, what are we going to get? Well, arg of z, if we approach this from above, then it's definitely going to approach 0. So we're going to have 1/4 and then 3 times 0, which is 0. And then how about arg of 3 minus z? What are the values of 3 minus z? Well, minus z will be on the interval minus 3 to 0. So 3 minus z will be on the interval 0 to 3. And if we're approaching from above, remember we have a minus z, which means that the imaginary part of the whole thing will initially be negative and reducing to 0. So imaginary part will be reducing to 0, which means that arg of 3 minus z will approach 2 pi. So plus 2 pi. So the argument function will be exactly 1/4 of 2 pi, which is pi over 2. And how about from below? Well, we're going to get 1/4. Arg of z approaching from below is still 0. Because remember, arg of z is defined on this interval, and if you approach this interval from below, then you're again going to approach 0. And how about arg of 3 minus z? Well, if you're approaching from below, z has a negative imaginary part and it's decreasing, but over here 3 minus z, the imaginary part of that will be positive and decreasing. So if we have a positive imaginary part on this interval and it's decreasing, then we're going to approach an argument of 0. So this is going to be plus 0. So the arg function will be equal to 0 in that case. Notice that's a discontinuous jump because e to the I pi over 2 is not equal to e to the I 0. Alright, so let's put that onto our picture. It's going to be useful later on. So approaching this interval from above, we're going to get pi over 2. And approaching from below, we're going to get 0. Alright, so after all that, what did we just show? We just showed that if we define the arg of z to be between minus pi, and arg of 3 minus z to be between 0 and 2 pi, because we need these two to define the natural logs of these things, then we're going to get a picture that looks something like this. So we have 2 branch points and then a branch cut running through right there, and everywhere else is continuous. Alright, so next step 2, we want to start constructing our contour somehow. So we know some information about this. I should also mention that there's going to be a singularity at 5 as well, because notice 5 minus x or 5 minus z over here. If you plug 5 in, then the denominator is going to be 0, which isn't good. So we have 0, 3, and then a 5. How do we construct our contour from here? Well, we want a path that kind of goes along this interval 0 to 3. So let's change marker colors just so you can see a bit more clearly. We want to include a path that kind of goes from 0 to 3. That's our goal. And the way we're going to do that is by constructing a Dogbone contour. So we're going to basically consider 2 paths that go like this, and then we're going to have some kinds of balls around each of these branch points. That's where the name Dogbone contour comes from. And we want to traverse this contour in the positive direction. So let's go this way, like so. And the reason why these 2 paths up here are so important is because that's where we're going to recover this I from. So I is our integral. That's where we're going to recover the value from. So let's call this top path over here psi1 and the bottom path psi2. And this first loop gamma1 and the second loop gamma 2. And let's actually call the whole entire contour C. So what we can say is that C is basically all these paths union together. So we're going to have psi 1 union psi 2 union gamma 1 union gamma 2. And what does that mean in terms of our integrals? What we get is the integral, contour integral along C, is equal to the integral along psi 1 plus the integral along psi 2 plus the integral along gamma 1 plus the integral along gamma 2. Alright, this is really quite nice because from these two over here we're going to be able to recover this I, and we can find what these values are later on, and all we have to do now is find out what C is equal to. Well, the problem with finding out what the contour integral over C is equal to is we're surrounding this branch cut, which isn't too great because we can't use Cauchy's residue theorem. But what we can do instead is somehow apply the residue at infinity, which I've derived in a previous video. And what we're going to be doing is imagine, let's draw a little picture up here, just so you can visualize it a little bit better. Let's say you connect some kind of bicycle pump to this contour, and you're going to be pumping this contour up. And what happens if you pump this contour up? Well, there's a couple of rules to have to follow. One, you can't cross any branch cuts or singularities because then the value of the contour integral will change. But if you pump this contour up, what you're going to get, let's just kind of draw things progressively. First of all, you're still going to have the branch cut and the singularities. If you pump it up a little bit, maybe it becomes a little bit bigger like so, and we have to kind of avoid this point at 5. Just remember that we can deform the contour as much as we want, and the value will still be the same. So if we pump this up a little bit more, what's going to happen? Well, maybe we're going to shape that looks like this. We still have to avoid this point at 5. But basically, as you pump it up bigger and bigger and bigger, the shape that we want to get is something like this. So we have the branch cut from 0 to 3, singularity at 5. The idea is we want to get a shape that looks like a really, really big circle like so. And then in order to kind of avoid this point at 5, we're going to construct some kinds of keyhole like so. So this is kind of similar to a keyhole integral, which I have dealt with in the past, but we also have this branch cut in here. So this is our goal contour, and this contour, well, it's still C. The value over this integral will still be the same. But notice that this C, we can decompose it into even more parts. Let's call this a big circle gamma. Let's call each of these kind of tunnel paths, I guess, maybe P1 and P2. And I'm going to call the little circle in here that's going around the points at 5, the singularity at 5, to be gamma 3. And remember, this contour C, we're traversing in the positive direction, so this is still going in the positive direction like so. So going to go in that way, and inside of the circle we're actually going to be negatively oriented, and we're going to go back out this way, and then this is a positively oriented contour. So let's deconstruct this contour into each of those singular paths. So now the contour integral over C is equal to the integral over gamma plus the integral over P1 plus the integral over P2 plus the integral over gamma 3. And notice that it's going in the negative direction, so I'm just going to indicate that by putting a negative up here. And notice one cool thing. We're going to be taking the limit as P1 and P2 approach each other, and they're actually going to cancel out, because notice the region that kind of surrounds P1 and P2, if you can kind of construct that region there, it's holomorphic, which means that the integrals are going to approach the same values but with different signs because they're going in different directions. So in the limit, P1 and P2 will cancel each other out to 0. And we're left with the integral over C is equal to the integral over gamma. And let's reorient this contour. So we're going to actually subtract the integral over gamma 3, but in the positive direction. Alright, so what did we just find? Notice that these two integrals are going to have the exact same values. We just deformed it without crossing any singularities. But we basically found two completely different expressions. This expression is nice because we can recover our I from here, from these two integrals. But this expression is also nice because on the integral over this big gamma, we can use the residue at infinity. So let's clean things up a little bit. This integral over C is now also equal to the integral over gamma plus the integral or actually minus the integral over gamma 3 but in the positive direction, but let's assume that everything's going in the positive direction, so we'll just leave it like that. So let's draw up a little bit of a picture. If this is the complex plane now, then the integral over gamma, since the paths of P1 and P2 will cancel each other out, we're just left with a big circle traversing the positive direction, so this is gamma, and then we also have this little circle gamma 3 in here, and this is the point at 5, and this is our branch cut that we had before. Alright, so how exactly are we going to evaluate each of these integrals? Notice that first of all, I kind of want to reorient this integral over gamma. Let's just reorient it to gamma negative. In order to counteract that, we're going to introduce a negative sign over here. Reason being is because, remember, the residue at infinity is defined as a contour that's going in the negative direction. Link up over here or in the description if you want to know how the residue at infinity formula is derived. But if we have a negatively oriented contour, we can apply the residue at infinity formula over here. So this is now equal to the residue at z equals to infinity of our function f of z. And then we have minus, well, the integral over gamma 3 is a small circle that only encloses the singularity at 5. So this also becomes the residue at z equals 5 of our function f of z. And remember, in order to go from integrals to residues, you also have to multiply everything by 2 pi I. That's just from Cauchy's residue theorem. So let's multiply all of this stuff by 2 pi I. And we now get this formulation. Alright, so let's go back over here. What I want to do now is I want to start solving each of these integrals. So let's go to step 3 over here. We're going to be calculating the integral over psi 1, psi 2, gamma 1, and gamma 2, like so. So let's find the integral. Let's do psi 1 first of our function f of z dz. What exactly is that? Well, we can parameterize this path a little bit. We can make a little bit of a substitution. So notice that z, every single z on psi 1 can be represented by some parameter t plus I epsilon, where t is on the interval 3 to 0. And I'm just writing it this way because we want to go from this right point to the left point. So starting at a real part of 3 and going to a real part of 0. That's going in this direction. And we also have to introduce this imaginary part of epsilon because we want to avoid the branch cut a little bit, and we're going to be taking the limit as epsilon approaches 0. So differentiating both sides, dz is equal to, now we're going to have just dt like so. Alright, so let's plug all of that stuff in. Now we're going to get the integral from 3 to 0 of f of z. So let's just use the definition of f of z. So that's going to be t plus I epsilon to the 3/4, and then 3 minus t minus I epsilon to the 1/4, all divided by 5 minus t minus I epsilon, and then dz is exactly dt, like so. And now let's reorient this integral a little bit. So this is the integral from 0 to 3 now. So, and then we're going to introduce a negative sign over there. And now what I want to do is, especially for this numerator, let's rewrite it in terms of logarithms. So this is now equal to minus the integral from 0 to 3 of e to the I, and let's apply the formula for the logarithm of complex numbers, because notice this whole inside is a complex number. So going to have e to the 3/4 natural log absolute value of t plus I epsilon, and then we're going to add that imaginary part, which is I times 3/4, and then argument of t plus I epsilon. So that's the first part, so the first factor, and then now for the second factor, we're going to get e to the 1/4 natural log of the absolute value of 3 minus t minus I epsilon, and then we're going to add the imaginary part, which is plus I times 1/4 arg of 3 minus t minus I epsilon, like so. And this is still all divided through by 5 minus t minus I epsilon, and this is dt. And notice that this looks very similar to what we had at the very start. We can just split everything up, split the exponentials up a little bit. And notice when we rewrite this, this first factor turns back into absolute value of t plus I epsilon raised to the 3/4. And then this second part becomes absolute value of 3 minus t minus I epsilon to the 1/4, and then we have this argument stuff going on up here. And then we're going to have 1/4, 3 arg of t plus I epsilon, and then plus arg of 3 minus t minus I epsilon, and this is still divided by 5 minus t minus I epsilon dt. And notice one thing over here, this argument function, if we just let t minus epsilon, remember that was our z. So this is, again over here is our z. Remember, if we take the limit as epsilon approaches 0, that means our imaginary part is reducing from above, which means we're approaching this branch 0 to 3 from above, which means that this whole entire argument thing, remember we drew this picture over here, the argument will approach pi over 2. So let's rub out this line over here, we don't need it anymore. The integral over psi 1 of a function f of z dz. If we apply the limit as epsilon approaches 0 on this thing, we're going to get a minus the integral from 0 to 3. If we just take the limit on each of these epsilons, won't really matter because we're in absolute values over here. So this is going to give us absolute value of t to the 3/4, absolute value of 3 minus t to the 1/4, and this argument part will approach e to the I pi over 2, just like we had up here, and over. Now 5 minus t minus I epsilon, we don't have branch cuts or anything going on down there, so we can just take the limit directly. This is 5 minus t and then dt, and so now this is equal to minus I, so this part over here, this is I, so minus I integral from 0 to 3. Notice that on the interval 0 to 3, everything in here is positive, so we just have t to the 3/4, 3 minus t to the 1/4, and then 5 minus t dt. And notice that's exactly our capital I that we started with, so this is minus I times capital I. So in fact, this first integral just evaluates to minus I times our capital I, like so. Alright, now we're going to be doing the exact same process for the integral over psi 2. I'm going to do this a little bit quicker because that did take quite a while to do. But the integral over psi 2 of f of z dz is going to be equal to, we can again parameterize it if we want to, so z is equal to t minus I epsilon, where t ranges from 0 to 3, and then we have dt is equal to dz. This is going to be equal to the integral from 0 to 3 of, now if we plug t minus epsilon into the z's over here, so we have t minus I epsilon 3/4, and then 3 minus t plus I epsilon to the 1/4, all divided by 5 minus t plus I epsilon dt. Again, we're going to transform all of this into logarithms, but I'm just going to skip a couple steps just to keep things short. So now we're going to have t minus I epsilon in absolute values to the 3/4, and then 3 minus t plus I epsilon to the 1/4, and then we're going to have the argument stuff up there, so e to the I, and then all that arg stuff there. But since we're approaching everything from below, this argument will approach 0, because remember, approaching this branch cut 0 to 3 from below will give us 0. So this is going to give us e to the I times 0 if we approach it from below, and this is 5 minus t plus I epsilon. And yeah, taking the limit as epsilon approaches 0, this is going to yield the integral from 0 to 3 of t to the 3/4, and then 3 minus t to the 1/4 over 5 minus t. E to the I 0 is just 1, and we get back our I. So in fact, the integral that's going below the branch cut will give us our original integral, capital I, back. Alright, so we've dealt with these two integrals. Now let's deal with these two integrals. And what I want to show with those two is that they approach 0 in the limit as their radius gets smaller. So let's take a look at the integral over gamma 1 first of our function f of z dz. We can again parameterize everything. Z is equal to, on gamma 1, notice that the radius is epsilon, and we have e to the I theta, because we're kind of going in a circle, and theta is going to range from, well, for psi 1 and psi 2, they basically kind of approach the branch cut, which means that if we deal with angles, it doesn't hurt just to consider the interval 0 to 2 pi. And then if we differentiate both sides, dz is equal to I epsilon e to the I theta d theta. So if we plug all this stuff in, let's actually take absolute value of this thing because we want to estimate it. This is going to be equal to the absolute value of the integral from 0 to 2 pi. And if we plug epsilon e to the I theta into all these z's, we're going to get epsilon to the 3/4 e to the I theta times 3/4, and then 3 minus epsilon e to the I theta to the 1/4, and then this is divided by 5 minus epsilon e to the I theta, and then our dz becomes I epsilon e to the I theta d theta, and the absolute value. And notice we're dealing with a real variable in here, which means we can use the integral inequality. So this is less than or equal to the integral of the inequality. So now we're going to get the integral from 0 to 2 pi. We're going to take the absolute value of all the stuff on the inside. But so first of all, epsilon to the 3/4 stays, and absolute value of this complex exponential function will just be 1, so let's ignore that. And then we're going to have absolute value of 3 minus epsilon e to the I theta to the 1/4, divided by the absolute value of 5 minus epsilon e to the I theta, and then absolute value of I is 1. Absolute value of epsilon is again epsilon, because we're assuming epsilon is positive, and absolute value of e to the I theta, that's just 1, so let's just end it off with a d theta. And notice we can combine these two epsilon terms together to get epsilon to the 7/4. And what I want to do now is I want to estimate this integral a little bit more. Notice that this numerator, we can find a new upper bound for that thing. Because notice that if theta is from 0 to 2 pi, that means we're just going in circles on this thing. And if we have 3 minus epsilon, and if we take absolute values of that, notice we have 3 minus this circle thing, so 3, and then we have a bunch of points that form a circle around it. If we're taking the absolute value, we're taking a look at the distance between the origin and each of those points. And what is the maximum distance between the origin and any one of those points? It's right over here, which happens to be 3 plus epsilon. So now we can say that this integral is less than or equal to the integral from 0 to 2 pi. Let's chuck this epsilon 7/4 out to the front as well. And this numerator is bounded above by 3 plus epsilon raised to the 1/4. And how about for the denominator? Well, we're taking the reciprocal of something, so ideally we want to minimize this denominator as much as we can to find an upper bound for the whole integrand. So if we have 5 minus epsilon e to the I theta, well, what does that look like? Well, we're starting at this point 5 over here, and we're just doing circles around it. And what is the minimum distance from 0 to any one of those points? Well, it's exactly this distance over here, which happens to be 5 minus epsilon. So 5 minus epsilon will minimize this denominator, which means that we can find a further upper bound to this thing, so 5 minus epsilon. And this is still with respects to theta. And notice everything inside of this integral, so the integrand is independent of theta, which means we can move it out to the front. So we're going to have epsilon 7/4, 3 plus epsilon to the 1/4, and then a 5 minus epsilon, and evaluating that integral will just give us a 2 pi. Alright, so what did we just find? We just found an upper bound for this integral over gamma 1. So let's rub all of this stuff out. We just found that this integral is less than or equal to epsilon to the 7/4, 3 plus epsilon to the 1/4, over 5 minus epsilon, and I guess I'll just stick the 2 pi out there. And what happens if epsilon approaches 0? So if we take the limit on both sides as epsilon approaches 0 on this integral, notice that if we take the limit on this right hand side, it's going to approach 0 because we're going to get 3 and then a 5, which are finite numbers. We're going to get 2 pi here as well, but this epsilon to the 7/4 is ultimately what's going to pull it down to 0, so this is less than or equal to 0. But notice we have an absolute value over here, which means that this is greater than or equal to 0, and the only way for this situation to occur, if something is less than or equal to 0 and greater than or equal to 0, is if it's equal to 0 itself. So that's a little bit of Squeeze theorem, like right there. So the limit as epsilon approaches 0, so this implies that this integral over gamma 1, absolute value of that is equal to 0, and the only way for the absolute value to be 0 is if the inside is 0, so that means the limit as epsilon approaches 0 on the integral over gamma 1 is indeed equal to 0. So in the end, this integral will evaluate to 0. And now we're going to be doing the exact same thing for gamma 2. It's not going to be too different, pretty similar actually. So let's take the absolute value of this. Let's start estimating. First, let's introduce a parameterization. So for all the z's on this circle, it can be represented by, actually, we're starting at 3, so we should have 3 plus epsilon e to the I theta, and dz is equal to, again, I epsilon e to the I theta d theta, and z is going to range from what we're going from here, which is minus pi all the way up to pi. So minus pi all the way up to pi, like so. Alright, so let's plug all of this stuff in. So now we're going to have the absolute value. Plugging this parameterization into all these z's, we're going to get the integral from minus pi to pi of 3 plus epsilon e to the I theta, but this thing raised to the 3/4, and then 3 minus this thing. Well, 3 minus 3 is 0, then we're going to have minus epsilon e to the I theta, but raised to the 1/4. And this is divided by 5 minus z. 5 minus 3 is exactly 2. And then we're going to have minus epsilon e to the I theta. And then dz becomes I epsilon e to the I theta, d theta. Again, we're dealing with a real variable, so let's use the integral inequality. This is less than or equal to the integral from minus pi to pi. Absolute value of this whole entire thing, what's that going to be equal to? Well, we're going to have 3 plus epsilon e to the I theta to the 3/4. Absolute value of this thing, absolute value will actually get rid of this negative for us. We're going to be left with epsilon to the 1/4. And then absolute value of this e to the I theta, again, that's 1. Absolute value of I is 1. Absolute value of epsilon is still epsilon, so let's add that to this exponent. So now we'll have 5/4. Absolute value of e to the I theta is 1. And on the denominator, we have the absolute value of 2 minus epsilon e to the I theta, like so, and d theta. Next, again, we want to find an upper bound for this thing. So let's rewrite this a little bit. So this is epsilon to the 5/4, integral from minus pi to pi. What's an upper bound for the numerator? Well, it's going to be 3 plus epsilon, that's an upper bound. So 3 plus epsilon to the 3/4, and then this is divided by, now we want to minimize this denominator as much as possible, and the minimum is 2 minus epsilon, and then then we have d theta, and now this is equal to, we can pull the integrand out because it's a constant. We're going to get 2 pi, because that's the integral from minus pi to pi of d theta, and then epsilon to the 5/4, 3 plus epsilon to the 3/4, divided by 2 minus epsilon. So that's our upper bound for our integral. So this integral is less than or equal to 2 pi epsilon to the 5/4, and then 3 plus epsilon to the 3/4 over 2 minus epsilon. And again, taking the limit on both sides, you can clearly see that in the limit as epsilon approaches 0, the integral over gamma 2 will be equal to 0. This epsilon to the 5/4 will ultimately kill off the whole thing. So we just found that the integral over gamma 2 is equal to 0. So that is step 3 done on this whole entire integral. We just evaluate the integrals over each of these paths, and there we go, those are the results. Alright, so we don't really need this picture anymore because we're finished with the integration. Now, step 4, this is going to be a little bit more spicy. Step 4 is going to be calculating these residues. So we've evaluated these integrals, now we just have to evaluate these residues. So let's find the residue at z equals 5 of our function f of z first. What's that going to be equal to? Well, if you look on our function f of z, at 5 we're going to have a simple pole. So I can just use the usual limit definition for simple poles. So that's the limit as z approaches 5 of z minus 5 times our function f of z, which is z to the 3/4, 3 minus z to the 1/4, divided by 5 minus z. And notice this factor and this factor here will cancel each other out, but we have to introduce a negative, so let's just stick that out the front. And in the limit as z approaches 5 on the rest, what's going to happen? We're going to get 5 to the 3/4, and then 3 minus 5, which is minus 2 to the 1/4. But notice minus 2, we can write that as 2 times e to the I pi. And remember, we're on this principal branch over here. So 2 times e to the I pi, this is raised to the 1/4, and this is equal to 5 to the 3/4, 2 to the 1/4, and then e to the I pi over 4. So that's going to be the residue at z equals 5 of our function f of z. So over here, let's put that down. This is going to be equal to 5 to the 3/4, 2 to the 1/4, and then e to the I pi over 4. Alright, so we've dealt with one residue. Surely the next residue won't be too hard. Spoiler alert, it will be a little bit different. We're going to be using quite an interesting method to find the residue. So let's find the residue at z equals to infinity now of our function f of z. Remember that in the previous video I showed that the residue at z equals infinity is the same thing as the residue at z equals 0 of 1 over z squared, but with a negative, and then f of 1 over z, like so. Alright, so now we want to calculate the residue at z equals 0. Let's just study this function first of all. So let's call that thing g of z, I guess. So g of z, what exactly is that? Well, we're going to have minus 1 over z squared over here, and then f of 1 over z. We basically plug 1 over z into all these z's, so we have 1 over z to the 3/4, and then 3 minus z to the 1/4, actually 1 over z, and then divided by 5 minus 1 over z. And you might say, well, calculating the residue at z equals 0 probably won't be too bad. You just apply that limit definition of the residue, but you have to be very careful in this case, especially because we have fractional powers. So you can't just use that usual limit formula that we have for the residue, because we can't in fact tell what order these poles are. What we have to do instead is we have to find some kind of Laurent series expansion for this function g of z, and then recover a specific coefficient from there, which is going to be the residue that we want. So let's muck around with this expression a little bit first. First of all, on this factor, I want to get everything on the common denominator. So this is now equal to minus 1 over z squared, and then we have 1 over z to the 3/4. Now we're going to have 3z minus 1 over z. So just putting everything on a common denominator, and then this is raised to the 1/4, and then over 5 minus 1 over z. Alright, now we can just split this 1/4 between the top and the bottom. So now the top will have 3 minus z to the 1/4, and the denominator will just have z to the 1/4 by itself. And notice z to the 3/4 and z to the 1/4 will produce z. So now we are left with minus 1 over z squared times 1 over z times 3z minus 1 to the 1/4 divided by 5 minus 1 over z. And now what we can do is we can distribute this z into this denominator to get rid of this fraction. So now we have minus 1 over z squared, and then we have 3z minus 1 to the 1/4 divided by 5z minus 1. But I also want to switch these two terms around, so we have 1 minus 5z, but we also have to introduce a negative, which will nicely cancel out with this negative in the front, like so. Alright, so we just showed that our function g of z, we can rewrite it a little bit in a bit of a better way. This is equal to 1 over z squared, and then 3z minus 1 to the 1/4 divided by 1 minus 5z, like so. Alright, and why did we want to get it into this form specifically? It's because we want to kind of transform this into some kinds of power series. And notice we have a 1 minus 5z on the denominator. That's really quite nice because remember we're calculating the residue at z equals 0. So all our z values will tend to be very close to 0, which means that it's going to be in the radius convergence of that of the geometric series. So first of all, let's write it over here. 1 over 1 minus 5z, we can write that as the geometric series. That's the sum. Let's use an index k going from 0 all the way up to infinity of 5z to the kth power. And we can rewrite this as 5 to the k and then z to the k. So this 1 over 1 minus 5z will give us a nice sum that we can work with. But how about the numerator? The numerator is going to be a little bit more interesting to work with because we have a fractional power. So 3z minus 1 to the 1/4. That's a fractional power, and what we want to do is use the binomial theorem in order to get the powers of z to be natural numbers or whole numbers. And the way we're going to do that, let's recall the binomial theorem. So if we have x plus y to the nth power, this is going to be the sum, let's use an index j, going from 0 to n of n choose j, and then we're going to have x to the n, x to the j actually, that's our index, and then y to the n minus j. Alright, notice over here we have a fractional power, so if we have x plus y to 1/4, then let's replace all our n's with 1/4, so 1/4, 1/4, and then 1/4. But the problem is, this sum is going from 0 to 1/4, which is really quite weird. But in fact, what we want to do is take the infinite sum from 0 to infinity. And basically the idea is whenever you have fractional powers, this is going to give you the power series. And I think there's a way using Taylor series to show that this is in fact the correct series expansion. But even in the case where our n is a natural number, if we just have x plus y to the n, it's still in fact technically an infinite sum. But the idea is if we have the 1/4 choose j, then we have an n choose j over here. And if you take a look at n choose j, n choose j is exactly n factorial over j factorial, n minus j factorial. And whenever j gets greater than n, if j is a whole number and it becomes bigger than n, then you're dealing with negative integers factorial, and those are all going to be equal to 0. And those are going to be poles. If you just look at the gamma function along the negative integers, you're going to have poles or places where it goes up to infinity. So 1 over infinity is going to give you 0. That's why we can just stop at n, because all the other terms are going to be 0 in the end anyways. But for the case of fractional powers, then you want to be dealing with an infinite sum. Alright, so let's take a look at this for a moment. If we have 3z minus 1 to the 1/4, let's use this formula. This is going to be equal to the sum running from j equals 0 to infinity of 1/4 choose j, and then we have x, which is 3z to the jth power, and then y, which is minus 1 to the 1/4 minus j. And well, let's rewrite this a little bit. This is the sum running from j equals 0 to infinity, 1/4 choose j, 3 to the j, z to the j, and then we have a minus 1 to the 1/4 minus j. Let's split up these exponents a little bit. So this is going to be minus 1 to the 1/4, and then minus 1 to the minus j, which is really the same thing as minus 1 to the j. And minus 1 to the 1/4, remember minus 1 is e to the I pi, but if we raise that to the quarter, we get e to the I pi over 4. So in fact, I guess I'll just put it on this line over here. This whiteboard is filling up a little bit too much. So overall, if we have 3z minus 1 to the 1/4, it's going to give us, let's bring this e to the I pi over 4 out to the outside. So e to the I pi over 4, and then we have the sum running from j equals 0 to infinity, 1/4 choose j, and then we have minus 1 to the j, 3 to the j, z to the j. So minus 1 to the j, 3 to the j, and then z to the j. And notice this is really nice to work with because now the powers of z are whole numbers. So let's combine these two sums together a little bit, not exactly combine them, but multiply them together to get what we have inside of our g. So our g of z, now we can rewrite this as 1 over z squared. And then let's put this first part first. So we have e to the I pi over 4. And we have the sum running from j equals 0 to infinity, 1/4 choose j, minus 1 to the j, 3 to the j, z to the j. And for our second sum, we're going to have the sum running from k equals 0 to infinity of 5 to the k and z to the k. So this is our new expression for g of z, and this is very messy to work with, but it's probably the best way to go about doing things because now we can directly recover our residue coefficient. So notice that this thing over here, that's going to give us some kind of power series. And we also have this 1 over z squared term over here. And remember, if your function f can be written as a Laurent series, so maybe you have something like dot 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 plus c minus 2 z to the minus 2 plus c to the minus 1 z to the minus 1 plus c0 plus c1 z to the 1 plus dot dot dot. The residue at z equals 0, because notice this Laurent series is centered around 0. So residue at 0 of your function f is exactly going to be the coefficient in front of the z to the minus 1 term. So this is going to be c minus 1. So you see here, over here we're calculating the residue at z equals 0 of g of z, which means that if we have some kinds of power series for g, all we need to do is find out what this c minus 1 coefficient is, which is the coefficient in front of the 1 over z term, and that's going to be the residue at 0. So how we're going to go about doing this over here. Notice that this is a power series, and later we're going to be dividing by 1 over z squared. So the only way for us to get the coefficient in front of 1 over c is to take a look at this other power series, which is in this case the product of two other power series, and find the coefficients, let's call it c, in front of the z terms. And by doing that, once we divide by z squared, it's going to give us the coefficient in front of the 1 over z term, which is exactly what we want. So our goal now is to compute what the coefficients are in front of the z to the first powers. And for this power series, this product of two power series, there's only two ways for us to get a term with the z to the first power. That's when for the first sum, j is equal to 0, and for the second sum, k is equal to 1, or j is equal to 1 on the first term, and k is equal to 0 on the second term. Because when we multiply those two together, z to the 0 times z to the 1 will be z to the 1, or z to the 1 times z to the 0 will still be z to the 1. So those are the only two combinations there, and all the other combinations will give us powers of z other than 1. So first of all, let's find what exactly is the value of the term when j is equal to 0. I'm going to switch in my blue marker because my black marker is running out from all this writing. At j equals 0, we're going to have 1/4, choose 0, minus 1 to the 0, and then 3 to the 0, z to the 0. And whenever you have something choose 0, it's always going to be 1. And notice all these are going to be 1 as well. So for j equals 0, you're just going to get 1. How about when k is equal to 1? Well, if you plug 1 into these k's, you're simply going to get 5z. And now what happens when j is equal to 1? Well, we're going to have 1/4, choose 1, minus 1 to the 1, 3 to the 1, and z to the 1. And whenever you have something choose 1, it's always going to be that something itself. So here it's going to be 1/4, and then we're going to have minus 1, so over here, and then times 3 times z. So over here, when j is equal to 1, we're going to get minus 3z over 4. And when k is equal to 0, let's see, we're just going to get 1. So that's pretty straightforward. Now what happens when we multiply these two together? Well, if we multiply over here, for the first combination, we get 5z. And for the second combination, we get minus 3/4 z. And suppose if we expand all of these power series out and multiply, FOIL it, or whatever, each of these rows will be different terms, and they will combine together to give us the whole power series itself. So we have to add it over here. So 5z minus 3/4 z, you can check for yourself, that's going to be 17/4 times z. So this is going to be the term with the z to the first power. So let's rewrite everything out. G of z is now equal to 1 over z squared, e to the I pi over 4, and then this power series, what's that going to become? We're going to have dot 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 plus 17 over 4z, and then plus higher order terms like so. So in the end, we can say that g of z, let's multiply 1 over z into everything, it's going to be equal to this power series, which is dot 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 plus 17 over 4 e to the I pi over 4 times 1 over z, because if we divide by z squared over here, we're going to get 1 over z, and then plus higher order terms like so. Alright, so that's our expression for g of z. It's not a complete expression for g of z, but this is all we really need, because if we're calculating the residue at z equals 0 of our g of z, we're simply going to take the coefficient in front of the 1 over z term, which in this case is going to be 17/4 e to the I pi over 4. I just realized I in fact forgot a negative sign over here, because this whole integral evaluates to the residue, but I forgot a negative sign. So there should be a negative sign right there. So this residue, we just found that it evaluates to 17/4 e to the I pi over 4. Alright, so I just cleared the whiteboard a little bit and rewrote everything because it was getting a little bit messy. But as you can see, we've basically got everything that we've shown thus far, and now it's time to combine everything together. So looking at the left-hand side over here, we can rewrite this a little bit. So minus I times I plus I, let's ignore these zeros, it's equal to minus 2 pi I times 17 over 4 e to the I pi over 4. That's the residue at infinity, and we add that with the residue at 5, but we have a minus sign, so we have a minus 5 to the 3/4, 2 to the 1/4, e to the I pi over 4. And notice we have an algebraic expression involving I, which is quite nice, so now we just have to isolate that somehow. So let's first factor the left-hand side. So now we have I, and then 1 minus I is equal to, let's see, we have minus 2 pi I, and let's factor out e to the I pi over 4. And now we are left with, on the inside, 17/4 minus 5 to the 3/4, 2 to the 1/4. And what I'm going to do now is try to combine these two fractions, these two terms together. So let's multiply the top and bottom here by 2 squared, which is 4. So divide by 4. And now let's take a look at the left-hand side once again. 1 minus I in polar form is root 2 e to the minus I pi over 4. And this is equal to, let's factor out the 4 as well to cancel out with this 2. So now we have minus pi I e to the I pi over 4 divided by 2, and we're left with 17 minus. Now let's combine these two 2's together, so 5 to the 3/4, and then 2. 2 is exactly 8/4, so 1 plus 8 is 9, so 2 to 9 quarters, like so. And now let's start moving things to the right hand side. So I is equal to, first of all, we have a minus pi I e to the I pi over 4, and multiplying both sides by e to the I pi over 4 to cancel out with this exponential over here. We're going to get another copy of that, and this is divided by, well, we have a 2, and we're going to get an extra root 2 down here, and then we have 17 minus, and now let's try to get things raised to the 3/4. Notice that this over here, we have 2 to the 9th, which is exactly the same thing as 2 cubed, but to the 3/4. And we can keep clearing things up a little bit. We're really close now. We're going to get minus pi times I. E to the I pi over 4 times e to the I pi over 4 is e to the I pi over 2, which is I, so double I, and then 2 root 2, and then 17 minus, now 2 cubed, that's just 8. So now we can use some indices, laws, whatever, to combine these two bases together to get 40 to the 3/4. And we are very close now. Let's just clean things up at the front a little bit. We are now left with I times I, which is minus 1, but we also have a minus out here, which will cancel out. So we're left with pi over 2 root 2, 17 minus 40 to the 3/4. And that is the final result for today's integral. So this is equal to pi over 2 root 2, 17 minus 40 to the 3/4. Bit of an exotic answer, but well, we have numbers flying around in there everywhere. So yeah, that's pretty much it for this video. It's been quite a long video. I'm guessing probably like an hour once I edit this all down. But yeah, I hope you guys enjoyed this video. It's a bit of an interesting approach to integration using this Dogbone contour and using the residue at infinity and all that. But yeah, until next time, hope you guys have a wonderful day, and I'll see everyone later. Bye bye.